Everybody is here, but as you know, I will start with the standard stuff that's always there. So our starting point is data. It's a vector with k elements given by some device. Then we need to have a good model for this data, and we call this the continuum model. There we want to make a mathematical description of what happens in the measurement process. The idea is that we write the vector m tilde as the result of some linear operator acting on a function or a physical quantity f beautiful that we are interested in. And inevitably there will be some kind of measurement error, some kind of random noise. And actually, of course, this equality is not perfect. I mean, this is only a model. Although it's a continuum model, it's only a model, whereas this comes from the real world. So this is also imperfect. So there are two kinds of error, data error and modeling error. Then, for computational regions, we need a computational model, because working with a computer to solve the inverse problem. The inverse problem is, given the data, find as much information as possible about f. Ideally, find f, but that's usually impossible, too much to ask for. But we can go close, we can approximate f as well as possible. And for this approximation process, we need to design a matrix model with a k by n matrix. Here, f being a vector in Rn, m vector in Rk, and here the idea would be that f approximates f beautiful in some nice sense. Either it's a collection of point values or maybe an expansion of f beautiful in some basis. And the matrix A is supposed to do what A beautiful is doing as closely as possible. So we have been looking at two cases, one-dimensional convolution operation and two-dimensional tomography. Those are our leading examples in the course. Okay, so then we have seen that sometimes the matrix A can be coming from an ill-posed inverse problem. In that case, A will have some kernel. The singular values of A become very small. The first one may be quite large, and the last non-zero one may be very small, bringing instability. So we can't really successfully apply some kind of least squares solution method. We need something that makes the inversion process robust against noise. So far, we have looked at truncated singular value decomposition and also Tikhonov regularization, both regular and generalized. Today, we'll take an extra step and look at so-called total variation regularization that's designed to promote jumps and discontinuities in the target. So it's supposed to result in piecewise constant reconstructions, also allowing jumps. The basic methodology is very similar to Tikhonov regularization. It's called variational regularization. It's kind of a term that covers both Tikhonov and total variation regularization. And here the idea is to take the argmin, so to find the vector in Rn that gives the minimum value of the following expression. And the expression is containing first a term related to data. So here we have the usual Euclidean 2 norm, the usual length of a vector computed by the Pythagoras formula, and the norm squared. Here the idea is that for a vector f, we perform simulated measurements by multiplying by matrix A. Then we compare the result to the data vector we are given. And if our f is giving really, really different measurements than what we measured, then this term will be large and maybe not close to the minimum we are looking for. The trouble with ill-post inverse problems is that there may be an infinite number of f vectors that give 0 value or values very close to 0 to this one, and kind of the same small values for a large number of f, maybe even an infinite number of vectors f. That's why we need something extra. That's the regularization part. So we add another kind of competing penalty. This is a penalty arising from data, and the other one is a penalty arising from a priori information, something we know about f apart from the measurement. Our starting point was to have, so there's an alpha is a positive real number. It's a regularization parameter giving a trade-off how much we emphasize this term versus the other one. And this was our first thing we looked at. This is Tikhonov regularization. And let me just write here that this is f1 squared plus f2 squared plus so on, fn. It's a real vector. I wouldn't maybe need this, but bear with me. I just have the absolute values there. They don't change anything either. And then we have we would have the square root here. Oh no, n 2. We would have the square root, but because of this guy here, we don't have the square root. So this is what we have for Tikhonov. But then we have other choices. Like we saw, another choice is generalized Tikhonov. For example, this one, where L, a typical choice, it can be many other things, but today we are thinking of L being a finite difference matrix. And in a very simple, writing it in a very simple form, we would just have f2 minus f1 squared plus f3 minus f2 squared and so on until the end, and kind of depending on the boundary values we want to enforce. Here I'm just taking fn minus fn minus 1 squared. So for example, this one we might have in the L matrix, we could have also the difference between the grid points to be more like a finite difference matrix, but let's not care about it. Let's just look at this simple case today. So
what did you call the L matrix?
Sorry?
What did you call the L matrix?
L matrix. Maybe I would call it a regularization operator. I think it will be a regularization operator or regularization matrix. And well, in this case, it would just be something like this. We would have minus 1, plus 1, 0, 0, 0, minus 1, plus 1, 0, and so on. So these two guys would go along the diagonal here. And then with total variation, the third choice, total variation, there we actually have the same thing, LF, but however we have one norm. Not the Euclidean usual 2 norm, but we have the 1 norm. And what does it mean? In this context, it's just f2 minus f1 absolute value plus f3 minus f2 absolute value plus so on, and the last one, fn minus 1 absolute value. So that's the one norm of LF. Of course, one could also look at just one norm applied to F itself. That's sometimes called impulse prior, and it's also useful in some cases. But in this course, we will mostly be focusing on the first derivative and one norm, which is the original total variation. And this idea was introduced by Rudin, Osher, and Fatemi in 92. It has been a wildly successful strategy. It has been studied so much since then. Many papers have been published about how to best compute such a minimizing element, the regularized solution. There are many approaches to that. We will be taking a look at 2 approaches in this course, but there are many more. Very effective. I mean, it's really a very active industry building good, effective computational methods for minimizing this. Also, it has been generalized in many ways. One example is so-called total generalized variation that I showed a little bit in the introduction of the course, which is, roughly speaking, when total variation favors piecewise constant targets, total generalized variation can be made to favor piecewise smooth targets. But that's a bit outside of the scope of this course. It becomes so technical. Yeah.
Just want to double check again. The first alpha, second norm, ff squared was Tikhonov.
Yes.
The last one was total variation.
Yes.
And what was the middle one?
This is generalized Tikhonov.
Right.
Yes. So Tikhonov regularization, generalized Tikhonov regularization, and total variation regularization, depending on what term we put here. Yep.
Couldn't you just generalize this and call it generalized LB regularization?
Yes. Yes, and it has been indeed used with other p values. For example, p strictly between 1 and 2, which is nice. It kind of gives a little bit similar things than total variation, quite different from Tikhonov. So already it gives a bit more discontinuous looking results while still giving a differentiable function to minimize, because that will be a central problem for us. These things here are differentiable, as you see, because of the second derivatives of the absolute value. But this one has a discontinuity of the derivative where the absolute value of function is at 0. So that's a central problem we have to deal with, non-differentiability of this one. But yes, and I think under the term variational regularization, there is actually a large collection of possible terms to put here. So in this course, we are kind of looking at the most classical one, and then the general, almost as classical, and then this is kind of more modern and very successful, but it also dates already to the 90s, so it's not the newest thing, but still pretty new. Yep.
Is this kind of this L matrix here, is it like a specific case, or can it be basically whatever, but this is maybe usual case, or is it always like that?
It depends on what kind of derivative you want to look at, because these things can be written also in continuum. So there's a lot of mathematics analyzing this formula really for this model in function spaces. So this course is so computational that we are really all the time paying attention to the discretized things and how they look. But there is a really big and successful theory behind inversion also in these infinite dimensional function spaces. And there it kind of depends on, are you penalizing the f itself, or the first derivative of f, or second derivative. And in higher dimensions, I mean, are you dealing with the gradient of f, or maybe applying the Laplace operator as a second order derivative, maybe higher order derivatives, or some kind of directional second order derivatives. There are a lot of choices, and each of those choices leads to a different matrix L. So yes, there can be a great bunch of L matrices, and in this course, for simplicity reasons, we kind of stick to the first and simplest case, the very basic finite difference approximation of the first derivative. And in the 2D tomography case, we will be dealing with the gradient. We have the gradient of f that then contains both horizontal and vertical derivatives of f. And in pixel images, it means horizontal and vertical differences. So there we actually need difference matrices both horizontally and vertically. But in this, let's do this 1D thing first to have everything as clear as possible. So somehow my thinking behind choosing this material is that with the Tikhonov, well, of course, it's so classical that the course just has to have it. That's the first thing to try in any ill-post inverse problem. It's a very powerful methodology, and there are very efficient computational methods of solving these minimization problems. So that's why, I mean, if you can get by with Tikhonov, great, that's good. Then use it and solve the application problem using Tikhonov, if at all possible. However, as we have seen and will see, Tikhonov favors some kind of smoothness in the reconstructions. And especially there's a term called edge preserving, meaning that if we know that our unknown has jumps and discontinuities, we would really like the reconstructions to have them as well. So that's why I want to include in the course something that kind of breaks out of that category of always giving some kind of smooth and regular reconstructions. I want to show you that it's possible to get some jumps out of it. So that's kind of the story behind this selection. And yes, there are many generalizations and other choices, and it's really an active field of research. A lot of things are happening. Okay, and maybe let me comment a little bit about the 2 norm and 1 norm thing. It's related to promoting sparsity. You may have heard about sparsity or maybe compressed sensing. Who has heard the term compressed sensing? A couple, maybe, yeah. How about 3? About sparsity promoting. Okay, some 5 or so.
Are there any Finnish words for those?
Sparsity is harvuus, harvoja ratkaisuja suosivat menetelmät. Compressed sensing, I'm not sure in Finnish. I'm not sure if there is. Maybe there isn't. Yeah, it's very new stuff. I mean, it's like 10, 15 years old stuff. So it's at most, and it's very active. So we are dealing with quite current research and quite new stuff. And with sparsity, the idea. Let me try to. Let's see how well can I do this. I'll try. So. If you just think we are solving a problem that has an infinite number of equally good solutions. Like we saw sometimes if the matrix A has kernel, our inverse problem can have that there will be some kind of a subspace or a full linear affine space or subspace with equally good solutions. So like we saw the least square, there may be many least square solutions, and then maybe we opt to pick the minimum norm solution. We looked at that kind of stuff a little bit. So in that kind of thing we might have, let's say, let's say these are all as good solutions to our problem. So based on the measurement information alone, we are not able to really pick out one of them. So then we talked about this minimum norm solution, and we can think of the minimum norm, finding the minimum norm solution. So we wanted the minimum 2 norm. So actually, out of all these vectors, we would like to choose the one that's closest to the origin in just the classical length, like the Pythagoras length. So one way to think about it is that let's draw spheres. So along a sphere, along each of these spheres, the 2 norm of all the vectors in the sphere are the same. Apart from my drawing skills, these are not perfect, but I'm supposed to be drawing perfect circles so that the 2 norm of the vectors in each circle is constant. So I'm kind of expanding a sphere as long as it hits this line, and then this one would be the minimum norm solution. And then if we have some uncertainty in the data, some noise, it may happen that if we have different noise, maybe our equation has some uncertainty, so it's not completely, when the noise changes, our set of solutions changes a little bit. And then you can see that if we change a little bit this line, then the minimum norm solution will a little bit vary there according to the noise. Okay, so this is the story of the 2 norm. Then we go to the world of sparsity and the world of compressed sensing, the world of using the 1 norm. And here I'm really talking about the 1 norm of the vector itself, so no L matrix here. We are just looking at the 1 norm of 2 vectors in this plane. So if this is x and y, then the 1 norm of a vector would be just x plus y. And here x squared plus y squared. So this is constant. In each of these circles, this is constant. And now I want to write sets where this is constant. And now again, we have our line here, and maybe there's a little bit of uncertainty where the line really goes, but somewhere there anyway. And again, we are looking for a minimum norm solution, however, using 1 norm, not the 2 norm. So what happens? As you can easily check, the spheres for this norm are not circles. The spheres for this norm look like this. Maybe in some analysis course you have looked at these LP balls with P ranging between 1 and 2. With 2 you get circles, with 1 you get this kind of things, and in between you get some kind of rounded corners, and rounding more and more becoming circles. And when P becomes larger than 2 and goes to infinity, the infinity sphere would be a box with horizontal and vertical sides. So these are LP balls. So now we are approaching by expanding these 1 spheres. And finally, we hit our solution set here. And now, even if our line is a little bit unstable under noise, you see, because of the shape of the sphere, even when the noise is moving, all of the points we hit will be on the y-axis. right? Sparsity means that a big portion of the elements of a vector are zero, exactly zero. So this is a very simple example of sparsity. For all the solutions we get for our minimum norm solution, the x-coordinate is zero, completely exactly zero for all of them. Even if we perturb the problem a little bit with the noise, even if our line is a little bit shaking and moving because of noise and instability, nevertheless, all the solutions we get will have x component exactly zero. That's sparsity. And of course it rises into its full glory only in higher dimensions when n in our problem is quite large, like we will compute later today with something like n is 64, 128 or something like this, or of course even larger. And then it will mean that somehow most of the elements are zero, and only here and there are allowed to be some non-zero ones. And this is a really powerful method. That's why in the case of the L matrix, which is the derivative, it means that the derivative is mostly zero. The components of this difference, the components are mostly zero. So when the derivative is zero, the function is constant. And in some places, in a small number of locations, the element may be something else than zero. For the derivative, it means there's a jump. So the derivative is allowed to have a few jumps here and there, and apart from the jumps, the result should be constant. That's what it means to be piecewise constant. Yep.
When you're talking about the jumps, is it like it's not discontinuity, but it's not defined, or?
Excellent question, excellent question. Again, when I talk about jumps, what is it really? Because for a function like this in the continuum model, if it's discontinuous, then the derivative doesn't exist at that point. This is, again, quite a deep question, and it would take us into a study of rather involved function spaces. Actually, it's full of many surprising analysis things when you really go into these spaces of functions of bounded variation and look at the norms of those and minimization problems in them. That becomes quite a technical journey into some serious mathematics. So let me say in the context of this course that we are looking at the discrete vectors, the Rn vectors, and there a jump means just there is a difference from one evaluation point to the next. And when this is zero, there is no change from one point to another. So let's keep it at that in this course. Sorry. Okay, let's break the video.